Hey everybody, today we're going to keep working with accumulation functions. And really for this video, we're just going to go through two AP questions from old tests. So you can start to see really what you're going to be asked to do for these type of questions on the AP exam. We're going to skip the question on page 4. I don't feel like that's the best question to go through to really understand this type of FRQ. So we'll go through starting here on page 5, and then we'll do one other problem. So let's go ahead and take a look. So here we have, it says the graph of the function f consisting of 3 line segments is given above, or really to the side here. And so what I always like to do is I'm going to label this f really clearly so that as I work through the problem, it's in my mind really clearly that this is f. Now, I've got the function g of x that's defined as the integral from 1 to x of f of t dt. So I want to be really clear. G is defined as the integral of f. My graph is of f. So let's see what they're asking us to do. In part A, they're asking us to compute g of 4 and g of negative 2. So for g of 4, I'm going to go here to how my function g is defined. So g of x is the integral from 1 to x of f of t dt. So since I'm finding g of 4, I'm going to actually evaluate the integral from 1 to 4 of f of t dt. And this, since we're evaluating an integral and we have a graph here, this is just going to be the area between the curve and the x-axis between 1 and 4. So as I'm looking, I notice a couple things. It looks like from 1 to 2, I'll just sketch this in here. So from 1 to 2, I've got a trapezoid there. So I'm going to take the height of my trapezoid is 1. So I've got 1/2 times my one base is 4. And my other base, it looks like, is 1. Now, I could add this area and then subtract this area, but what I know is those are congruent triangles, so their areas are going to cancel each other out. So really the area between the x-axis and my curve is just this portion here. So if I simplify that, that's just going to be 5/2. So that's the value of g of 4. Okay, so now for the next one, I have g of negative 2. So g of negative 2, again using my definition of g, is the integral from 1 to negative 2 of f of t dt. Now, what I notice first is that my order of integration here is backwards. So I'm going to change that. Again, we know if we change the order, we have to use the negative. So now it's the opposite of the integral from negative 2 to 1 of f of t dt. Now, from negative 2 to 1, here it looks like I just have this triangle. So I have negative 1/2. My base is going to be 3. Sorry. And let's see, the height of my triangle is 4. So that value is negative 6. So that's part A, just showing the computations for how we calculate g of 4 and g of negative 2 using areas. All right, so now for part B, it's asking us to find the instantaneous rate of change of g with respect to x at x equals 1. Well, I know if I'm finding the instantaneous rate of change of g, that's just our derivative. That's g prime. And if I want to find that at x equals 1, what I want to find is g prime of 1. So now, I know, I'm just going to go back here. If I want to find g prime of x, I know that's just the derivative, right, of our function, which is our integral of 1 to x f of t dt. And hopefully by now it's become automatic. We should recognize that when we're taking the derivative of an integral, that's just our fundamental theorem. So I know since my lower limit's a constant, upper limit is x, that derivative is just f of x. So in other words, g prime of x is just f of x. So if I want to know what g prime of 1, well, that's just f of 1. Now, since my graph is of f, I can know that f of 1 is equal to 4. All right, part C. I want to find the absolute minimum value of g on the interval from -2 to 4. And we're going to justify our answer. So let's see. If I want to know where the minimum is, I know I need to look at, let's see, I'm looking for the minimum value of g. So I need to take the derivative of g, which we already said in part B. I know the derivative is just equal to f of x, and I want to know where that's equal to 0. So if I look at my graph, I know that f of x is equal to 0. I'm going to make a little table here. It's equal to 0, -2, and at 3. Okay, and then I'm just going to include my endpoint, 4. So there's my table. Now, I know if I'm looking for minimum, I'm looking to see where my graph changes from negative to positive, where g prime. So if I look at g prime, which I know is f, g prime is going to be positive wherever it's above, f is above the x-axis. So that tells me from -2 to 3, that's going to be positive. Okay, g prime, which is equal to f, is negative where it's below, which is between 3 and 4. So now, I actually notice I have a max at x equals 3. So since I'm increasing from -2 to 3 and decreasing from 3 to 4, that tells me my minimum values are going to be at the endpoints. So that's the first thing I'm going to make a note of. Okay, since g is increasing -2 to 3 and decreasing on the interval from 3 to 4, I know that the minimum values occur at the endpoints. So now, to figure out which one has the absolute minimum value, let's scooch this up, I need to actually calculate the values of g of -2 and g of 4, so I can compare those values. So let's see, g of -2. Well, the nice thing actually is that we already calculated g of -2 up in part A, and that's what a lot of these problems will do. They'll have you reference values you calculated earlier. So I know that g of -2 is -6. So I know I have -2, -6. And let's see, g of 4, excuse me, we also calculated, and we know that's 5/2. So 4 5/2. All right, so since g of -2 is less than g of 4, we know that the absolute minimum occurs at -2. Now, we have to be careful for what the question's asking. It wants to know the absolute minimum value. So they want to know not the x value where it occurs, but the actual y value. So I'm going to say, since g of -2 is less than g of 4, the absolute minimum value of g on the interval from -2 to 4 is -6. Let me move this over so you can see that. Okay, so the absolute minimum value of g is -6. So since they asked for the value, they want that y value. All right, last piece here now. Okay, it says the second derivative of g is not defined at x equals 1 and x equals 2. So if we think about this, g double prime of x Well, since g prime of x is f of x, I know g double prime of x equals f prime of x. So if we think of the derivative of f, it makes sense that it's not defined at x equals 1 and x equals 2 because we have corners, so we know we're not differentiable there. So those are potential candidates for points of inflection. So this question is asking, of those values, which ones are actual points of inflection of the graph of g? So here's what we're going to do. We know that g double prime of x, right, is undefined. Let's say I've got my endpoint, so -2. We know we're undefined at 1, and we're undefined at 2. And so I need to see if we actually change concavity at those points to determine which one is a point of inflection. So if I'm looking at g double prime, which is f prime of x, I know that I'm going to be positive where the slope of f is positive and negative where the slope of f is negative. So if I look at my graph, I know that the slope of f, so f prime, is positive between -2 and 1, and negative everywhere else because this has a negative slope. So in terms of my table, it's going to look like this. I'm positive, and then negative everywhere else. So the only place I change concavity is at x equals 1. So I can say inflection point occurs at x equals 1 because this is the only value where, let's see, make sure, yep, where g double prime of x changes sign. We don't have an inflection point unless that changes sign at that value. All right, so let's go ahead and take a look at one more of these accumulation function problems on the next page. Okay, so this one comes from the 2003 AP test. Okay, and so here we go. We have a function f defined on the closed interval from 0 to 7. The graph of f consisting of 4 line segments is shown in the graph here. And again, we have a function g that's defined as an integral. It's an integral from 2 to x of f of t dt. Okay, so again, we're asked to find some function values. And so here again, keep in mind, if g of x is defined as our integral, then g prime of x, we know, is the derivative of this integral. Again, that's our fundamental theorem, and I know the derivative of this integral is just going to be f of x. And then that means that g double prime of x equals f prime of x. And that kind of helps me keep my thoughts organized a bit as I go through these problems. So the first thing we want to find is g of 3. So I know that g of 3 is the integral from 2 to 3 of f of t dt. And so here, to evaluate this integral, I'm just going to use my graph and use my area formulas. So from 2 to 3, I can see I have a trapezoid here. Its height is 1. So I have 1/2. Base 1 is 4. And my other base is 2. So if I simplify that, I get g of 3 is 3. Okay, then g prime of 3. Well, we said g prime of x is f of x, so g prime of 3 is just going to be f of 3. I'm going to read that right off the graph, and f of 3 equals 2. Okay, then lastly, we have g double prime of 3, which I know is f prime of 3. F prime is just the slope here, and since I have a linear piece, I know I have a constant slope, which is going to be -2 over 1, or just -2. So there's the values for part A. All right, so now part B is asking for me to find the average rate of change of G. When I see average rate of change, I'm thinking slope formula. Right? We're not looking for a derivative here. That would be the instantaneous rate of change. Since we're looking for average rate of change, we're just using slope. So on the interval from 0 to 3. So if I want average rate of change, I know that's just going to be g of 3 minus g of 0 over 3 minus 0. Well, we got a little help from up above. I know that g of 3 is equal to 3. Now I just have to go ahead and quickly calculate g of 0. Well, g of 0 is the integral from 2 to 0 of f of t dt, or the opposite of the integral from 0 to 2. And let's see, if I use geometry, I've got a triangle there. So I have 1/2 times 2 times 4, and so that value is 4. Oops, I can't forget my negative. So it's actually a negative 4. So now I have 3 minus a negative 4 over 3 minus 0. So it's 7/3 is my average rate of change. Okay, so now Part C wants to know for how many values of C, where C is between 0 and 3, is G prime of C equal to the average rate of change in Part B. Now, this should sound familiar. This is one of our theorems. So it's asking me, where is my average rate of change equal to the instantaneous rate of change, which is my derivative. So I'm going to make a note here. This should make you think of our MVT, our mean value theorem. That was all about finding where the derivative, our instantaneous rate of change, is equal to the average rate of change. Now here, they're not asking us to find the values of C. They just want to know how many places that happened. So now we have to remember our average rate of change is 7/3. Right, so a little more than 2. And let's see, I know G prime of C, well, that's just equal to f of x. So what I want to know is how many places is f equal to 7/3. So we can think here of drawing a horizontal line. I can see in the interval between 0 and 3, I intersect the graph of f 2 times. So I would say there are 2 values of C where G prime of C, which is really equal to f of C, is equal to 7/3. Okay, and I know that because the line y equals 7/3 intersects the graph of f two times in the interval from 0 to 3. So again, they're not asking for us to solve for those values. They just want to know how many that there are. Okay, now the last part is asking about points of inflection. So they want to know the x-coordinate of each point of inflection of the graph of G on the interval from 0 to 7, and we need to justify our answer. So again, I know for points of inflection, I'm looking for where G double prime of x, which is equal to f prime of x, is equal to 0 or does not exist. So essentially what this means is on my graph of f, I'm looking for places where the slope is 0 or it doesn't exist, so it's not differentiable, maybe to a corner or vertical tangent. All of those issues could cause me to cause that derivative to not exist. So if I'm looking at my graph here from 0 to 7, I can see 3 points here at 2, 4, and 5 where we wouldn't exist due to a corner. So those are my possible points of inflection. at 2, 4, and 5. So now I need to look at what's actually happening here. So G double prime, let's see, I'm going to check my endpoint here, and then I've got 2, 4, 5, and here's my other endpoint, 7. So I need to describe what's happening here. Okay, so let's take a look now. I know that G double prime is going to be positive wherever the slope of f is positive. So looking at my graph, it looks like between 0 and 2, I'm going to be positive, and then between 5 and 7. So I'm going to put that in my chart. And then all the way here between 2 to 4 and then 4 to 5, I'm negative everywhere there because that slope is negative. So now I can see that I had change sign at 2 and I change at 5. So I know I have points of inflection occur at x equals 2. And I'm going to say because G double prime equals F prime changes from positive to negative. Okay, so it occurs at x equals 2 because I changed sign from positive to negative. And I have a point at x equals 5 because G double prime equals F prime changes. Oh, let me move this up, sorry. Changes from negative to positive. Okay, so that's two examples of what these will typically look like on the AP test. And you'll have some time in the next class period to be working through some on your own and get help and ask questions as needed.